So in this video, we're going to talk about what are called indefinite integrals, where we use integration in order to find what we've been calling the antiderivative. Now, some people, some books, some forums use the finding the antiderivative and using integration sort of interchangeably. Some books, some forums, some teachers are like, no, there is absolutely a minimal amount of overlap and they are not interchangeable, but in these videos, I'm considering them interchangeable. So keep in mind that if your book or your instructor is not of that persuasion, okay, they may not see them as interchangeable words. But to me, asking somebody to find the antiderivative and asking them to integrate it if it's an indefinite integral are the same thing. Okay, so we're going to use that approach. Now, what you're going to learn is a new notation for something that you've already been doing. So you're going to see this little symbol that looks kind of like an S. Mine get kind of less curly as we go through, but it's kind of like this. All right, so do the best you can with that shape, and you have you're going to, that's the integration symbol. Okay, and you'll see that on all sorts of different kinds of software that you're using to do the math. So we're going to integrate some function, and this is the typical definition that they use. And this is sometimes confusing for students. Sometimes it makes my head hurt, and I'll tell you why in just a second. So this is called the integrand. This is the differential. Remember, we had a video on differentials earlier. And it also identifies which one's the independent variable. So, and the way I phrase it is this one wins. Okay, so if that's a dx and over here you have something else like t's or y's or whatever, everybody has to be a dx, it has to be an x. If this was a dt, everybody has to be a t. So this is a little tiny thing, and you'll understand why I'm talking tiny in the next video. But it's the most powerful one. Everybody has to match that. Okay, makes sense later. And so, but what happens is in what we're doing when we took the antiderivative, we had a derivative, right? They gave us a derivative and they wanted us to back it up and find out what the original function could have been, or at least a family set of functions, right? And so what we're used to is that f prime was the derivative and f was the original function, right? We'd go back to f. And what's confusing a lot of times is, I don't know why, okay, they use f here, but this is actually the derivative of something. And they're asking you to find the original function over here. So this would be trying to find the original function. That you took the derivative of and got this. So since we've been so ingrained that f prime is the derivative, suddenly calling f the derivative makes your head just sort of go, no, not go in there. So I frankly don't think of it as f and capital F. I think of it as f prime and capital F, but and maybe that's just, I don't know why that is. Maybe because I'm not a true math major, I'm an engineering major. But I'm sure that the math teachers that used to work for me would complain if I didn't write it this way. So this is what we do. But they can't get you for what you think. All right. So think of this as I'm going to integrate some sort of derivative and try to retrieve the original function. Okay, same thing as finding the antiderivative to me. Now, so just to compare, what you would have seen in the past is if I told you that we took the derivative of something and got 3x plus 2, and I asked you for the antiderivative, you would have then called it f. And you would have said, oh, these are just x's are constants, so I add 1 to the power, divide by the new power. And if it's a constant now, it was a 2x, and I have some unknown constant I can't retrieve without further information. And if you've stumbled onto this video and you don't remember how to do this part, you need to go back and look at the first antiderivative video. Okay, now we could have also phrased it as dy dx is 3x plus 2. And you might have told me that y is 3x squared over 2 plus 2x plus c, right? There's all sorts of different ways to ask a question. Now what we could have done is to say the integral of dy is 3x plus 2 dx, right? That differential format we used to use. And then you would say, well, the integral of dy is y, and this is 3x squared over 2 plus 2x plus c. Now, at this stage of the game, we're not usually doing this part. They're just having you say, can you integrate this part? And you would get this. Okay. But later, much later, not in this video, right? Then we'll have equations or differentials setups that we're going to do where you have the two sides. Do this in engineering all the time. Okay. So that happens later, but not so much right now. All right. Now, what we're going to do for right now is to stick with what happens if somebody just walks up to you and on a piece of paper says, can you do this? Now, this is what's called an indefinite integral. If it was, and we're not doing this today or in this video, but if you was from 2 to 3, that's called a definite integral because we're looking at a certain section of the function. But when there's not any numbers or variables in these locations right here, then this is an indefinite integral. We're going to get a general type case like we did with the antiderivative where we get a family functions where we retrieve part of the function except for the constant, so we go plus c. And we would say this is 3x squared over 2 plus 2x plus c. Okay, so this is the format that we're going to be dealing with for a while. All right, now I'm going to show you a couple of the really simple ones where you just have an x or a constant or a multiplier. And we're just going to do just a couple so that you can kind of get used to this notation system. But the main emphasis of this video is the more complicated ones, which are called the use substitution. And these are ones that if we had been taking the derivative of it, we would have needed the chain rule to get it done. Because remember when we first started taking the derivatives, we would say take the derivative, y is equal to 3x squared plus 4x plus 6. We would say take the derivative of that. That was no problem. Use the power rule, right? But if you had y is equal to 3x plus 6 cubed, you had to use the chain rule, right? So things that would have required the chain rule to take the derivative, we have to use the use substitution to back it up. And it's a little weird, but it's kind of fun. If you like puzzles, it's not too bad. All right, so we're just going to do a couple of these. If you're a little rusty on this part of it, you need to go back and look at the Antiderivatives 1 video, and this will take you through everything you wanted to know about backing up the typical power rules and trig functions that didn't require the chain rule. Okay, so if they ask me to integrate 4x cubed plus x to the 2/3 plus x to the minus 2, each of these is just an x, right? X to a power with numbers as coefficients. You can think of this, but you don't have to write it down like this. But what you're actually doing is going 4x cubed dx, x to the 2/3 dx, and x to the minus 2 dx. You're going to integrate each piece. Notice that this is an x raised to a power dx. You know, in effect, this x right here, the derivative of x is dx. Okay, it's actually 1 dx. All right, here we go. So here's an x, here's a dx. So just kind of note that on the way through. But this is the typical section that we did when we worked lots of antiderivatives. So you'd have 4x. You'd add 1 to the current power, so 3 plus 1 is 4, divided by the new power, plus x. Add 1 to the new power, so 1 added to 2/3 is adding 3/3. Pen doesn't want to make 3/3. 3/3. So that would be 5/3. And you're going to divide by 5/3, which is the same thing. So if you divide by 5/3, it's the same thing as multiplying by 3/5, multiplying by the reciprocal. Dividing by a fraction is multiplying by a reciprocal. Again, if you want to see that in more detail, go back to that first antiderivatives video. And then you'd add 1 to the power, divide by the new power. Don't forget the plus c. So then these 4's cancel, and you have x to the 4th plus 3/5 x to the 5/3 minus x to the minus 1 plus c. And that's the result of this operation. All right, now, sometimes, remember when we took the derivative, I said it's normally good form to return the answer in the same format that the question was given. And since this had negative exponents, this has negative exponents, that's okay. But again, the one with the red pen wins, whether that's your computer graded homework system or your teacher graded homework system or test system. If they don't want negative exponents in it, no matter how it was given to you, the one with the red pen wins. Whoever's grading, whatever they want you to do, that's what you do. All right. Now, let's do another one that's pretty straightforward, and then we're going to do the u substitution. So if we have 3 cosine x plus 2e to the x minus 3 over x dx. Remember that it's like the dx is applying to each one. And so most people, but not all, tend to do that part in their head mentally. They see it individually. I just wrote the same thing down again. Let's back that up. Okay, dx plus 2x. That's what happens when you start thinking about the next thing you want to say. Happens to teachers all the time. All right, now here we go. So this, remember, is the derivative of something else that we were taking the antiderivative to find. So what do you take the derivative of to get cosine? Because this is not where you add 1 to the power. This is a recognition. You have to recognize the pattern. Well, we must have taken the derivative of sine, right, to get cosine. And the coefficient just drags along. Okay, plus 2. What did you take the derivative of to get e to the x? It was e to the x. I love e to the x. It's just the fact that it's itself again just makes me smile every time. Minus. Now we have a 3. And this is actually 1 over x, or x to the minus 1. So do you remember in the antiderivative section we talked about if you added 1 to the power and divided by the new power, you're actually dividing by 0, right? Which is not allowed. So if you have 1 over x, or x to the minus 1 that you're going to integrate, then you have to recognize that pattern as well and realize that it must have been a natural log, because the derivative of the natural log of x is 1 over x. So some of these are recognition patterns, and if you don't know the pattern well enough to recognize it, you're kind of having to go back really and review those. And for the ones that you don't recognize, if you just sort of found these videos right here at this point, there's a whole bunch of videos on how to take the derivatives of different things. So if you're rusty on this, you might want to go back and look at the derivatives, since that's what we're going to be backing up. All right, but let's talk about, what if we have x plus 2 squared dx? Now, when we first started taking derivatives, we didn't know how to do the chain rule. So what we would do is we would expand this out and go, okay, I can square x plus 2. That'd be x squared plus 4x plus 4. Then I'm going to integrate each one. So I add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. 4x, right? Plus c. So this would be 1/3 x cubed, excuse me, plus 2x squared plus 4x plus c, right? Now, what we can also do now, and I'm just going to get you to try to trust me for just a second. Kind of a dangerous thing, right? All right, is I want you to think of, I'm going to try to show you the use substitution before we actually get too far into it, just so that you can see how it goes. So what would happen is, let's say that this, because we would have taken the chain rule to find its derivative, right? So let's say that this is u, all right? So if u is going to be x plus 2, then the derivative of u with respect to x is, well, the derivative of x is 1, the derivative of 2 is 0, so du would be equal to 1 dx. And the 1 is kind of understood to be there, right? So you can think of this as 1 dx right here, so this would be du. So this is of the form u squared du, which, if you think of a u as just a variable like an x, I don't have to do the chain rule on that. So this would be, to do this, you would add 1 to the power, divide by the new power, plus c. And then go, well, wait, it wasn't really a u originally, it was an x plus 2. And if you expand this out, and I'm not doing this in my head, I did it on a different piece of paper, but I used to be able to do this on my head. And when you clean this up, you get 1/3 x cubed plus 2x squared plus 4x plus 8/3 plus c. But these are constants, right? Now, look right here. So look between here and here. So do you see the 1/3 x cubed plus 2x squared plus 4x plus c? And so this c looks different, but it's just a constant. Just like this is a constant. So a constant that we don't know is as good as a constant plus 8/3 that we don't know. So do you see how this is going to kind of work out? I just wanted to show you that you're going to get to the same location. An alternative way to sort of explain this is to say f of g of x times g prime of x, integrating that with respect to x, gives me back my original function in terms of g plus c. Some books use this description. So this is saying if you have a function in terms of u, du, you can integrate it and get the original function in terms of u and then switch it back out. Okay, so that's what we're doing. It's easier to do than it is to kind of try to set it up in an equation. Now we've got a whole bunch of problems to work, so let's just get started. And here we go. So 25 secant squared 3t plus 1 dt, because it doesn't have to be x's, right? Now, you look at it over and you go, okay, in here, the argument for the trig, it's not just a t, it's a 3t plus 1. So if you were going to take the derivative of this again, then you would have to do the chain rule, right? So backing it up is probably going to be the chain rule in reverse. So let's do the u du thing. So you have to pick something for u. It's usually the part that has the powers in it. And that gets iffy when they're all got powers in it. So but it's at the inside. You know how when you did the chain rule and you were going, take the derivative of the outside, loop back in and take the derivative of the inside, right? Or leave the inside alone, loop back in and take the derivative of the inside. That inside part, that's u. All right. So u is 3t plus 1. And I'm going to walk through this really slow. It really is easy, better for you to do this, but a lot of students do not take the derivative with respect to t this time. And that's okay as long as you know what you're doing, but at some point, if it gets more difficult, you probably need to do this if it's very complicated. And if you haven't been practicing doing this, then it's hard to kind of come back up with it. All right. So practice it until it's really comfortable, and then if you want to give it up, you can always pull it back out. So if I can get it in terms of u du, all right, then I'm good. So you look back over here and go, I am looking for 3 dt. That's what you're trying to build. And you go, well, I've got the dt, but I don't have a 3. Well, that's pretty easy to fix. You just multiply by a 3. Now, can we really do that? I mean, is that algebraically allowed to multiply something by 3 and have it be equivalent to what it was before? Well, no, okay, because now it's 3 times bigger. So to undo that, we immediately come out here and undo it. So the 1/3 on the outside multiplied by the 3 on the inside is really negates each other. It becomes 1. But now I have my du. So this here is du. And this is secant squared u. See the pattern I'm going for? All right. So let's go back to here. And I have the integral of, and I'm going to pull the 25 out in front. 25/3 secant squared u du. See the pattern? So this is my u, this is my du, and now it's a much simpler problem, right? So what did you take the derivative of to get secant squared? Because this is the derivative of something. Well, you took the derivative of tangent. Okay, so this is 25/3 tangent of u plus c. Okay, so the u du says I'm good, right? So this, but they didn't ask me about that. They didn't ask me about u. They asked me about 3t plus 1. When I change variables, I sometimes keep trying to do x. I wonder if that happens to you. And so this is the answer to this. So you remember in algebra where you used to change the change of variable technique where you changed it to u and then changed it back? It's like that. Okay, let's do another. X sine x squared dx. Now you're looking for u and du. You could make u be x, or it could be this x squared. But remember, it's something you're going to loop back in as the inside. It's typically the inside part. And du is going to be a power less if you're dealing with powers. So I'm not thinking this is u. I'm thinking this is u. So if we let u be x squared, then du dx is 2x. So du is 2x dx. So I'm looking for this over here, right? Now I have the dx. Oh, and I actually have the x over here, but I don't have a 2, right? So what this is going to be, I'm going to rearrange it a little bit, is sine x squared. I'm going to bring the x they gave me over here, dx. So this x is going to come over here. And I need a 2. So I just go, oh, 2 times that. No big deal. As long as I immediately undo it by multiplying by 1/2 on the outside. So this is du. This is sine of u. It's not u squared because u is x squared. So this is sine of u, right? Sine of u du. So this is 1/2 integral sine u du. Okay, what did you take the derivative of to get positive sine? Well, remember when you take the derivative of cosine, you get a negative sign, and I don't have a negative, so I must have had a negative to start with. So it's negative 1/2 cosine x squared. Let me stay with u. I just switched it all out for you. U plus c. And remember, they didn't ask us about u, so it's x squared plus c. And that would be the answer to this. Now, some of your teachers don't make you do a complete sentence, and by complete sentence, I mean left-hand side equal to a right-hand side answer. Some do, right? Some will just let you string the equals down all the way and then box in the answers. But this is the way I was trained. All right, so this is what we're doing. Now, what you can do is, if you did this correctly, if you take the derivative of this part right here, it should get you back to here. All right, so it wouldn't hurt you to check that. And in fact, if I was on a test and was trying to save points, I would check every one. I would come over here and go, okay, minus 1/2 cosine x squared. Remember, the derivative of c is going to go away. So you'd have negative 1/2. The derivative of cosine is negative sine. Leave the inside alone. Loop back in and take the derivative of the inside, right? So these two negatives make a positive. This 2 and this 2 cancel, and you have x sine x squared. Let's do another one. So we have the integral of x over x squared plus 1 squared dx. Now, you can either make u be the x, u be the x squared plus 1 squared, or u could be x squared plus 1, the inside. So do you want u to be the whole thing? I don't think u being x would be a good choice, because what am I going to do with the mess that's underneath? All right. If you do this whole u is equal to x squared plus 1 squared, then du is going to be something like 2 x squared plus 1 to the first times 2x, and that would require me to have another x squared plus 1 in addition to the one I've got, which I don't have. So I hope that this will make more sense. If you'll come back and read and listen to this part again when we get to the end, what this is saying is, if you were going to use this part right here, you would have to have an additional x squared plus 1 x squared plus 1 in there, not just the original one. This one would have to be an extra. And we don't have an extra one. All right, so I'm thinking u is going to be x squared plus 1. So du dx is 2x. Du is 2x dx. All right. So we look back over here, and we've got the dx part taken care of. We've got the x part taken care of. We just need a 2. So we put a 2 right here, and we immediately undo it. Okay. So what I'd have is 1/2, and I'm going to integrate x squared plus 1 to the negative 2 to x dx. It helps me to get my u stuff all together, okay, instead of leaving it mixed up around everything. So this is my du, and this is u to the minus 2. So I'm going to be integrating 1/2 u to the minus 2 du. So this is just the power rule. So we have 1/2 u, add 1 to the power, so that'd be a -1 now, divided by the new power, plus c. So this is -1/2 u to the -1 plus c. So this is -1/2 x squared plus 1 to the -1 plus c. Now sum will let you stop right here. And sum will say, all right, I need it back in the same, as close as you can get to the original format, which was a fraction. So it'd be 1/2 x squared plus 1 to the first plus c. Just depends on what you're being asked to do. Now, sometimes students go, okay, is the 1/2 applying to the c? You know, is the c actually part of the 1/2? Well, half of c is still just a c. So since we don't know what it is in the first place, just put it on the outside. All right, let's do a couple more. Actually, we need to do a bunch more. It's going to be a long video. But I think it's better to do a whole bunch of these and have you be comfortable with it than to do just a few and have you not be comfortable. All right. Now remember that sometimes it was more helpful when we did the chain rule to actually show what was going on with this shorthand version. So this was cosine x to the 4th of sine x dx. And I think this one is pretty easy for you to decide which one's u, because this is definitely the thing raised to the bigger power. So let's let u be cosine of x. Then du with respect to x, taking the derivative. The derivative of cosine is negative sine. So du is negative sine x dx. All right, so I am looking for that up in here. So I go back up in there and go, well, all I'm missing is a negative, right? So all I need to do is to have a negative in here, right there, and then undo it out there. So this is going to be the negative of, and remember cosine x is your u, so this would be u to the 4th du, because this was du, right? All of that was in du. So this is going to be the negative, and u would be added 1 to the power, divided by the new power plus c. So it's going to be the negative 1/5 cosine to the 5th x plus c, because remember u is cosine x, right? Okay. Anytime you want to stop, I guess, watching the video, you can, but these are going to get more and more complicated as we go. Got a lot to go. All right. I just want you to be really comfortable with this. You do this a lot for the rest of your calculus career. And so if you get lost on this or never quite catch on to what's going on, it's like you're just lost for the rest of the time. For the majority of the time, it's pretty bad. All right. So I just think it's important to do it that way. Now, let's clean this up just a little bit, because sometimes just changing the appearance makes it really obvious about what's going on. And I remember derivatives didn't understand roots, and integration doesn't either, so they do powers. Okay, so I changed this to 1/2 power, and then to pull it up to the top, it's a negative 1/2. Now remember, what happens is it's the part that normally you loop back in and then get a derivative of that. So do you see how this is the biggest powered portion. And if you think about it, this derivative of x squared plus 2x is a version of x plus 1. So we're going to use u being x squared plus 2x minus 4, right? So it's usually an inside part of something. And if you're looking at it going, then your first guess should be the one with the higher powers, because you're going to take the derivative of this and get lower powers, right? So du is 2x plus 2 dx. Now this is just slightly different variation because this is more than what you want. Normally you're missing pieces from du, and this is like more. Okay, so what you can do is to say, well, I still need this. This is x plus 1, this is 2. So I can still do the 2 here. By more, I meant there's too much in here than what you're looking at, x plus 1. You had to factor it out. So I can put the 2 up in there, but I'd have to immediately undo it. Okay, so what this is going to be is 1/2 x squared plus 2x minus 4 to the negative 1/2 2 x plus 1 dx. Okay, you doing all right? Okay, sorry. So this is du, u to the negative 1/2. So this is 1/2 u to the negative 1/2 du. So 1/2, add 1 to the power, that'd make it a positive 1/2. Divide by the new power is to divide by a half is to, well, let's just put a half down there for right now, plus c, because this half is going to cancel this one. So you have u to the 1/2 plus c, and u was x squared plus 2x minus 4 to the 1/2 plus c. That looks a little bit better than it started, didn't it? All right. We're getting there. Here we go. E to the x plus 1, e to the x plus x. And you're like, well, they're both kind of crazy. Okay. So I have two choices. I could let u be this one, in which case I'm hoping this is du, or I can make u be this one, and this would be du. Which one would be considered like the highest power? Because they both have an e to the x in them. So that's kind of equivalent, because the derivative of e to the x is the e to the x, so that's not helpful. But this one has an x, and this one has a 1. And the derivative of x is 1, so I'm thinking this one would be the u, because technically it's kind of the highest power, because it's got an x. So if u is e to the x plus x, du dx is derivative of e to the x is e to the x. Derivative of x is 1. So du is e to the x plus 1 dx. So this is already up there, right? What you have is the integral of e to the x plus x, e to the x plus 1 dx. This is du, this is u. So you've got the integral of u du. Very simple. Looks very simple this way. So add 1 to the power, divide by the new power. So this is e to the x plus x squared over 2 plus c after we change it back from u to the original variable types that we changed out. All right, integral of 5x cubed root of 1 minus x squared dx. Now, if I was you, you might want to stop the video, and see how you're doing, kind of do a spot check. Do this one, see if you get get an answer. You'll get an answer if you don't stop, and then come back and see if you got the same thing. So stop it and come back. And so, assuming you're back, I chose u to be 1 minus x squared. After you did your du dx thing and then moved the dx over, you should have gotten du is minus 2x plus times dx, all right? And so that's a little weird, right? Because I have a 5, but that's not helpful. So I'm going to pull the 5 out. This is 1 minus x squared to the 1/3, because remember, they don't like roots, they like powers. And then that would leave me just my x and my dx over here. And so what I need is a negative 2 dx. All right, so assuming you're back, you would have u is equal to 1 minus x squared is what I chose. Du, after you went through these mechanics, is minus 2x dx. And so what you need to do is to rearrange over here. We don't really need the 5, so let's pull that out in front and change this up just a little bit. Remember, they like powers, not roots. So this is what I've got right now, and I need a negative 2. So hopefully what you did is you put a negative 2 in there. And then you have to undo it by out here multiplying by a negative 1/2. Right? You just undo what you just did. So this turns out to be negative 5/2 u to the 1/3 du. So this is negative 5/2. You add 1 to the power, and you would have u to the 4/3, and then you would divide by 4/3, which is the same thing as multiplying by 3/4. So I'm going to skip a step because it's getting kind of long. So you'd have minus 15 over 8. And then substituting in there for u, you'd have 1 minus x squared to the 4/3 plus c. Now, some teachers will let you stay there, okay, because technically 1 minus x squared to the 4/3 is the cubed root of 1 minus x squared to the 4th, and 3 goes into 4 one time with 1 left over. Okay, so technically this is how 1 minus x squared to the 4/3 cleans up. And I don't know if your teacher wants you to do that or not, but if they do, that's what you do. It's sort of like when you write English papers, some teachers like flowery and lots of prose and I don't know, all sorts of neat stuff. And some people just want cut and dried to the point. And you dealt with that with your English teacher. Okay, so math teachers same way. Some want it one way, some want it another way. Here's another one. Okay, e raised to the sine of pi x cosine of pi x dx. All right. Now, this is where you sort of have to be careful. That doesn't look like a pi. Well, you should be careful all the time. But if you let u be the entire thing, e to the sine pi x, then du, remember the derivative of e to anything is itself. Okay, loop back in and take the derivative of this. So it'd be cosine pi x times pi. And that would require you to have you've got cosine of pi x, but you would have to have this. Again, this would have to be separate. It cannot be included in the original one. Okay, so you would have to have this original one, and then you would have to have a separate e to the sine pi x, which you don't have. Okay, so be careful. Sometimes the mind wants to reuse the original as this part right here, and you can't do that. Okay, so u is going to be sine pi x. Everybody has their one function. They don't get double used. Okay, they don't get used in two places at the same time. All right, so du dx, derivative of sine is cosine. Loop back in and take the derivative of the inside. So du is cosine pi x pi dx, right? So we look at this, look over here. Now, this is going to be e to the u. And this is really close to my du, except I need a pi in here, right? So what I need is e to the sine of pi x cosine of pi x. I need an extra pi right there, so I undo it. Okay, so this is 1 over pi e to the u du, because all of this is du, and this is e to the u, right? So how do you do it? What's the derivative of, this is kind of like e to the x. What's the derivative of e to the x? E to the x. What's the integral of e to the u? E to the u. Okay, so this is 1 over pi e, and e is sine of pi x plus c. And if you're not sure about that one, take the derivative of it. Take the derivative of this and see if it gets you that. And it does, doesn't it? My engineering teachers would not like my boxes. All right. I'm thinking I might skip the next one I was thinking about doing. Let's do this one. The integral of 4x cubed plus 6x squared plus 4x plus 6 cubed, 24x squared plus 24x plus 8 dx. I think you can kind of tell which one's u. It's the biggest powered part on the inside. So let's let u be 4x cubed plus 6x squared plus 4x plus 6. So du dx is 12x squared plus 12x plus 4. So du is 12x squared plus 12x plus 4 dx. All right. Now what you've got is 24x squared plus 24x minus 18. So let's talk about that a minute. Can you think of this as 2 times 12x squared plus 24x minus, let me take out the 2 here too, plus 12x minus 9. Let me go back up here. This is supposed to be an 8. I just can't read my own writing. Beg your pardon. So I'll give you a minute to correct that. All right, dx. So this is what I want. I don't need the 2, right? That 2 is actually kind of too much. So we're going to take the 2 and pull it out here. So this is 2. And all of this. So this is du, all of this. And this is u cubed. See it? So this is 2 times, and we're going to have the integral of u cubed du. So this is 2 u to the 4th over 4 plus c. So this is 1/2 u, which is 4x cubed plus 6x squared plus 4x plus 6 to the 4th plus c. Barely made that fit. All right. Now, hope that's kind of, you're feeling much better about this and like, okay, yeah, I got that. It's because now we're going to try a variation, and I'm going to show you 2 of these variations, then we're going to be done. So it's going to go a little over an hour, but hang in there with me, all right? So while we're kind of on a roll about this, all right, we're going to do, let's integrate square root of x to x minus 1 dx. Okay? Now, I think, and I think you'd agree, that u must be 2x minus 1. All right? So if we do that, then du dx is just a 2. So du is 2 dx. Well, that's not a problem. I just put a 2 right here, and I undo it right there, right? The problem with it is this one has an x that I don't actually want to have, right? Because right now I'm comfortable with this as u to the 1/2 du, right? The question is, what am I going to do with that other x? Because you can't have a mixture, right? If you're going to switch them to du, everybody has to be a du. Remember at the start, I said this little part right here wins. If it's dx, everybody has to be an x. If it's du, everybody has to be a u. So how can I get a u from an x? We haven't done one of those before. And you're like, well, okay. Well, right here. You said correctly that u is equal to 2x minus 1. Well, if that's true, then isn't u plus 1 equal to 2x? I mean, it can't be false if you set it up as being true. So x would be u plus 1 over 2, right? So the thing that you set up for u, if you have an extra variable, see if you can get that extra variable in terms of u, and then substitute that in. So what you're going to have is 1/2 integral. And x, remember, is u plus 1 over 2. That's what this is. And this is u to the 1/2. And this is du. So that's this part, and that's this part. You with me? Okay. So this is 1/2. And I can multiply that out. I would have another one. I could pull out this 1/2. And you would have u plus 1 times u to the 1/2. So u plus 1 times u to the 1/2 is u to the 3/2 plus u to the 1/2 du. So this is 1/4. Pulling this 1/2 out here. And then you would, this is 3/2. So you would have integral of u to the 3/2 plus u to the 1/2 du. So this is 1/4. And when we do this, we would have u add 1 to the power, which is 5/2, divided by 5/2, which is multiplying by 2/5, plus u add 1 to the power, divide by 3/2, which is multiplying by 2/3, plus c. So this is 2, this 2 goes into 4 twice. I shouldn't do that because we're going to multiply the 4's both places. All right, so this is 4, and this is 2. So what we're going to have is 1/10 u to the 5/2 plus 1/6 u to the 3/2 plus c. So this is 1/10 2x minus 1 to the 5/2 and 1/6 2x minus 1 to the 3/2. And you can factor out this 2x minus 1 to the 3/2 and get a very I was playing around with it, and I got it down to where it was like 1/2 2x minus 1, 2x minus 1 to the 1/2, 1/5 2x minus 1 plus 1/5. I'm not sure that looks any better, so I thought, okay, not going to go there. All right, it cleans up a little bit better because of this, and you'd be back to a product, because what you had originally was a product, but most teachers are not going to make you take it back that far. If you need me to work that one all the way out, just write me a note or something. I'll append this. But I know you're getting tired, and we only have one more problem to do, and so let's scoot along. All right, same thing, x squared square root of x plus 1 dx. All right, so if you say u is x plus 1, du dx is 1, du is 1 dx. Now that's not a problem. I've already kind of got and understood one right there. Okay, but if I'm going to switch this to du, everybody has to be a u, and I've got an extra x squared, right? So taking it this way, u minus 1 is x, right? So I can substitute that in there, and I would have u minus 1 squared. So this is my x. This is u to the 1/2. That's this part. And this is 1 dx is du. So what I have is u minus 1 squared u. Make it just a little bit cleaner so you can see it. Now you cannot multiply this inside, all right, because remember your rule of order of operations, you'd have to do parentheses and exponents first before you can multiply. So we'd have to expand this out, and this would be u squared minus 2u plus 1 times u to the 1/2. So this is the integral of u to the 5/2 minus 2u to the 3/2 plus u to the 1/2 du. We haven't integrated yet. Sometimes students get lost in this and they think, oh, I've changed the powers. And I'm going, no, you haven't integrated yet. All right. So now we're going to say, all right, we have a u, we add 1 to the power, so that'd be 7/2. Divide by 7/2 or multiply by 2/7 minus 2 u, add 1 to the power, divide by the new power. Okay? Plus u, add 1 to the power, divide by the new power, plus c. So this is 2/7 u to the 7/2 minus 4/5, that's a minus, u to the 5/2 plus 2/3 u to the 3/2 plus c. Now, what you can do is to try to factor out the u before. So let's give that a try, rather than on the other problem where I was factoring that out at the end. So if you factor out the 2 that's in common and the u to the 3/2, which is the smallest powered one, you'd have 1/7 u squared minus 2/5 u plus 1/3 plus c. So this turns out to be 2x plus 1 to the 3/2, 1/7 x plus 1 squared minus 2/5 x plus 1 plus 1/3 plus c. And this one right here is actually the square root of x plus 1 cubed. And so this is actually x plus 1 times the square root of x plus 1 because 2 goes into 3 once with 1 left over. So any variation of this may suit your teacher, but I'm more interested in how are you doing with these take u and get du and also get another variable in terms of u, that kind of bi-directional thing. All right, so this would be the integral of x squared square root of x plus 1 dx. Actually looks much worse, doesn't it, than what it started. I kind of liked it before. All right. There you go. Now, so this is the u substitution for an indefinite integral. Again, if this is like, oh my gosh, my ability to integrate it all is compromised, go back and look at that antiderivatives 1 video. I'll actually put the link in there in the description just in case you need it. Don't forget that in the description there'll be a lot of problems for you to practice. Good practice. All right. And then the worked out solutions. And then, of course, the links to the next and previous videos. So in the next video, we're going to talk about Riemann sums. Okay, one of my favorite things to do, probably one of the least favorite things students do, but they remember it forever. So Riemann sums are important. It's a good concept for a lot of what you're going to do in the future. So you really need to understand Riemann sums. And not that you actually quite do them all the time, but you really need to understand them. And then we're kind of closing in on the end of what's a typical Calc 1 class. So don't forget to look at the description. Don't forget to like and subscribe. And see you in the next video.